Good morning, everyone. I hope you're doing well. Over the next couple of days, we're going to be talking about fission and fusion. So, these are reactions that are occurring on the nuclear scale and that have the potential to release a great deal of energy. So, before we begin, think about where does that energy come from? And for this, we're going to look at the concept of energy mass equivalence. And in fact, you might recognize this concept from your vocabulary list this week. The ideas that we're about to look at are all made possible by the theory of relativity. Now, you may have heard of this. This is the theory that Albert Einstein proposed in the early 1900s and that upended the physics world. It replaced Newton's, or Sir Isaac Newton's, theories and basically improved on them. It wasn't that Newton's theories were wrong, but it turns out in some cases they were approximations that no longer worked, especially when you had large gravitational fields or you were going close to the speed of light, etc. One of the key ideas behind the theory of relativity is this famous equation, maybe one of the most famous equations there is, E equals mc squared. And while many of us may have seen this equation before, you may not understand or realize what it actually means. Now, the science and math that went into the way that Albert Einstein came up with this equation is pretty complicated and hard to follow, but the equation itself is so elegant that it's a great starting point. We don't have to understand everything that went behind the equation, just what does it mean? For this equation, E equals energy, M is the mass, and C is the speed of light. And then, of course, it's squared, so it's to the second power. So let's think about what that means. Essentially, what it's saying is that for any given item, such as a paperclip or a penny or a car or a plane or anything, you take the mass of that item, essentially how much of it is there, how much stuff is there, and you could, in theory, convert that directly into pure energy. The mass would disappear, the energy would appear, it's all the same thing. It's really a profound idea to think about. So let's try a sample question. What would happen if we converted 1 gram of matter into pure energy? 1 gram is about the weight of a large paperclip, or maybe a teaspoon of sugar, so not very much. The speed of light is about 30 billion centimeters per second, or about 671 million miles per hour. So the energy equivalent of 1 gram of matter is 1 gram, that's the M, times 30 billion centimeters per second times another 30 billion centimeters per second, because it's C squared. And that gives us 9 with 20 zeros behind it, ergs of energy. All right, so an erg of energy is a fairly awkward unit that we don't use very much. So let's convert that into something a little more practical to understand. If we took one of the old-fashioned, inefficient 100-watt light bulbs, not the fluorescent type, not the LEDs, but the types that we used to use and we're trying to replace because they use too much energy. Well, let's say we have one of those that uses 100 watts. That's a pretty typical size. We could power that light bulb for approximately 30,000 years with that one paperclip worth of matter. In other words, we're talking about a lot of energy. It turns out that all of this energy is pretty difficult to release. You don't see paperclips exploding into massive, massive explosions very often. At least I hope we don't. And so that's probably a good thing that it's hard to release. But we have figured out a couple of ways that we can do it. One way is nuclear fission, and another way is nuclear fusion. Over the next couple of days, we'll be talking more about the differences. They're both nuclear reactions, however. So in the diagram to the right, we have a typical nuclear fission reaction with uranium-235. This is what's happening in nuclear power plants and atomic bombs, actually. Whenever we make this reaction occur, the neutron comes in, hits our uranium nucleus. It briefly turns into uranium-236, which is highly unstable, and so it splits up. 2 different parts, 141 barium, krypton 92. And then we have 3 neutrons come out of it. If you are able to measure the weight of each of these really, really precisely, something that you'll notice is there's actually a very tiny bit of mass that disappears. Now, we know that mass can't really disappear, so what's actually happening is that very tiny bit of mass is turning directly into pure energy. And that's where all the energy in the nuclear reactions come from. We're actually converting mass to energy, although it's a very, very tiny fraction of the mass. But remember, we're talking about a lot of energy, so that's how it ends up being so powerful. In fact, a typical nuclear reaction, such as fission or fusion, releases about 1,000,000 times more energy than a typical chemical reaction, such as combustion, like when you burn firewood, or like here on the left, if you detonate a TNT bomb, versus on the right with a fusion reaction, a hydrogen bomb. Most of the energy released is either heat or electromagnetic radiation, sometimes called EM radiation. Basically, here's our electromagnetic spectrum, and so it's going to be released in different ways. Radio waves, which is what we use to listen to the radio. Microwaves, the same waves that we use to cook with. The visible light that we see. The UV radiation that we worry about with sunburn. X-rays, like what we receive at the doctor's office. And gamma rays, the most energetic type of radiation, and in fact it's fairly dangerous. If we get hit by gamma rays, they can be quite damaging to our bodies. This is a really important concept because the sun, which is a great big giant fusion reaction, is releasing all this electromagnetic radiation. And what's convenient about electromagnetic radiation is that it can travel through space. And that's how the Earth ends up being warm. Without it, we would be a very cold place. So that basically concludes our introduction. We're going to be talking about these concepts more over the next couple days.